So as you mentioned, what I'm going to present now today is an overview of the EVEREST project. What is EVEREST? Well, EVEREST it's a project that has been founded last year under the call Big Data Technology and Extreme Scale Analytics. And the focus of the project is mainly around the topics that we heard today several times. That is about data processing and the use of FPGA accelerators inside data center. The main key idea of EVEREST is not only the acceleration of single function libraries that then can be on FPGA that can be used by larger code, but is to face the problem or understanding how to make the FPGA acceleration easier and working into a larger workflow to the end user. So here in the slides, you can see on the bottom some keywords that are behind EVEREST that are, of course, all around the concept of hardware acceleration, because as I mentioned before, despite its big data project, the key point is to understand how to manage heterogeneous resources, in particular FPGAs in data centers. The project touches problems from the software perspective, so in terms of domain-specific extensions to high-level synthesis, of course, to bring the modules easier on the FPGA, but also it takes care on the dynamic part, so considering the context of data centers, so including virtualization and dynamic adaptation, but also topics related to data security and the management and collection of data. Well, I know that it is a boring part, but as I mentioned before, EVEREST it's a large European funded project with several partners coming from different entities. The point is that the project is coordinated by IBM and by Politecnico di Milano, that also has the scientific management. Well, actually, I'm not the coordinator of the project from Polimi, but I'm one of the board member of the project. The coordination from IBM Zurich is from Christoph Agarter, while for Polimi it's Christian Pilato. Together with IBM and Polimi, technologies within the project are also brought by USI, the Università Italiana, that is mainly related to the security part, TU Dresden, and a group of Hieronymo Castrillon that is here also among the organizers, that is related to the part on domain-specific extension. There is Virtual Open System, a French company that is working on the virtualization context, and there is IT4I, that is a supercomputing center from Czech Republic that is not only providing HPC infrastructure, but also libraries to manage large workflow. And last but not least, we have a group of partners that are mainly related to applications, to the use cases that we are, real life use cases that we are going to face within the project to try to validate the concept and the technology that are produced by the first set of partners. In particular, we have a CIMA that is related to the weather prediction model, Duferco Energia, an Italian company from the renewable energy side, Numtech from France, that is a company related to the monitoring of air quality on industrial sites, and Sygic, that is a well-known company also for intelligent navigation, that in particular will manage the use case on intelligent transportation in smart cities. Before moving on, I want to say only a few words about where we are today. It's a sort of motivation of EVEREST. So we saw this at the beginning of the workshop, a very nice talk by Nuria that was explaining and providing a lot of data about where we are in the concept, where we are right now. So we know that we are in a data-driven world. We saw in the recent year a large increment of data that are produced every year. So this is a older projection from 2018 that shows how the production of data is increasing across the years. And we are in 2022. We can also say that there are in 2021 we produced 79 zettabyte. That is one year ahead of this projection that was made in 2018. So the production of data is even larger. So the reason why this happened is because in the early, I want to say, 20 years ago, the data produced were mainly by human, and nowadays most of the data are not produced by human, but are mainly produced by machines. This incrementing data as pros, so as positive aspects, so we can know everything that is happening everywhere. So it can be considered pros, and there are also cons in this direction. But in our case, there are problems due to the fact that even if we produce data, those data are not always used for several reasons. And the two well-known problems in data is that we have the so-called dark data, that are the data that are produced, but no one is going to process, are stored maybe somewhere, but there is no one that knows what to do with those data. That is for several reasons, because well, you don't know what to do with the data, but there is also the fact that in some cases there is no computing capability to process those data and extract useful information. And on the other side, we have the problem of the possibility not to store all the data that have been processed across the year, because, well, first of all, because there are not enough storage devices that are produced every year that can fill the gap of new data produced from one year to the other one. So this is something that we have to take care. So this is also the reason why there are this computing continuum. So there are computations that are moved to the edge, so where the data is produced, in order to reduce the amount of data that then can be processed and sent to the data center to be stored. Where EVEREST enters into this picture. Well, EVEREST is a project that tries to improve the efficiency in data computation, so to try to reduce the amount of data that need to be stored, because the computation can happen at runtime at a higher speed, and also improves the possibility to have less dark data, because there is this additional computation that is provided by FPGA. So, given that, what is the outline of the talk? So I will not be too much detailed as it was the previous talk by Zero, by Tobias, and so on. It will be much more high level. But what I'm going to show you today is something related to the EVEREST use cases. So what are the problems that we want to solve within EVEREST, or at least the cases that we want to face with the technology of the project. We are going to see some specific target architectures that are part of the project, and at the end we are going to have a quick look to the what we call the system development kit of EVEREST. That is the technology that is going to help mapping the use cases on the target architecture. Of course, trying to solve the problems that have been the challenges proposed by the use cases. Well, we are in the workshop on data-driven application for industrial and social challenges, and I think that the application that are within EVEREST are exactly well fitted with this topic. We have 3 use cases in EVEREST that are that have some constant. inside them. So all of them are looking for hardware acceleration. So most of the partner are, or most of the application use case, and the partner that brings the application use case are totally, they totally don't know how to start with an FPGA, but they want to explore, to try to see what are their possibilities that are offered. So there is a big push on the programmability, on solving, on easy or simplify the life for the programmer in order to exploit this technology. All the use case has some part that are related to machine learning, that involves machine learning based decision making, which means that are machine learning kernels, which means that there are problems that are related to the nowadays workloads that are mostly machine learning. And also, as I mentioned before, what those use cases are not simple kernel executions, but are more complicated pipeline that need to be orchestrated across the data center or the supercomputing center. What are those applications? What we are talking about? So we have two use cases that are related to, we want to say to weather forecast, or at least they takes as input a weather forecast. So this is also linked to the previous talk. One of the use cases about the monitoring of the air quality in industrial site. The second one is related to the estimation, to the prediction of the production of renewable energy in a wind farm. While the third one is related to the modeling of traffic in smart cities for intelligent transportation. Let's go a bit into the details so that we can understand a bit more what are the challenges that those application brings to the project. Well, the first, we don't start with one of the use cases, but we start with a sort of brick that is used in two use cases, both the one on the air quality in industrial sites, and also the other one is related to the renewable energy. Both use cases start with the first step that is based on the weather forecast, and in particular within the project, we have the CIMA Foundation that has in charge the management of the WRF. With the WRF application. WRF is a weather forecast model that is widely used in US centers, and it's a complicated project composed by several modules, and the request. And the request and challenges that we have on this first step of the two use cases is the fact that from the CIMA side point of view, they are interested in understanding how it is possible to have an automatic deployment of the several instances of the model on HPC resources, typically because the type of workload is mostly an HPC one, considering different boundary conditions. So that's a multiple submission in order to make to build a more reliable modeling output. And this is I would say that the larger request is to understand if it is possible to have an higher resolution model, considering the usage of FPGA resources. So to see if there is an advantage and when. If in the usage of FPGA, so the people from CIMA never had the possibility to use FPGAs, and they want to know how it is possible to use, of course, without writing the entire code in VHDL or Verilog for the WRF. Starting from this first step, the real use case. The real first use case of the project is what we call the air quality use case. So the idea is that we have a company that is Numtech that has a platform that want to predict the air quality in industrial site. The reason it's clear And this is mainly due to the fact that the industrial side want to be in some way notified if there is a sort of prediction that in short time maybe the quality of the air becomes worse, becomes under a certain threshold, because there is an impact also on the citizen. And the idea is that if there is a prediction that the air quality becomes under threshold, then there are several actions that can be done at the point of the industrial side. As an example, reducing the emission, maybe reducing also the production of the specific site, and so on. So of course you can imagine that those type of action had an impact that is on the financial side, because reducing the production means that you are losing something in the production capability of this industrial plant. And on the opposite, it's not only about the industrial plant, but it's also about the citizen, because if there is a wrong prediction on the other side, so the citizen are going to live with a bad air quality. So the objective here is to minimize the false predicted peak in the worst in the air quality, so in the minimum of the air quality, so say, and to optimize the number of real predicted peaks, so in the positive on the other side, because we want to reduce the production when it is needed. Of course, as you can imagine here, there is one of the key parts is the meteorological forecast, because it's not only the industrial plant that increase the emission when it increase the production, but there is also due to the fact that if there is wind or there is not wind, the amount of pollution remains around the area of the industrial plant. What are the requests by this use case? First of all, the request is very simple and say, okay, we want to improve the speed of the produced forecast in terms of weather prediction. This is a request that is not done on the technology, but is mainly done on the application. So they want a higher speed, weather forecast that in an indirect way requires that work will need to be accelerated. On the other side, they require also with a more complex workflow, they want also to improve. They are not interested in the prediction of the weather on a larger area. They're interested in the prediction on the local area that is close to the industrial side. And they want to do this by performing a sort of ensemble weather prediction aggregation, so using different sources of forecast, plus considering some data that are coming from local observations, so from sensors that are in the area where the plant is. And this, of course, it's they want to do a certain ensemble by using some machine learning technique. Last but not least, the final workflow is the one that put everything together in trying to produce the actual prediction of the air quality, because the idea is that starting from the output of the second workflow, then the problem is to try to understand actually what is the air quality in the area. And this is not only due to the weather forecast, but it's also due to the forecast of the emission of the industrial plant in the next period, and also other information that comes from the topology of where the industrial plant is located. And all those predictions need to be done at considering the specific site. So it's not general, but also the machine learning model that can be used. It depends strictly on the site where this prediction is done. So if you want to monitor multiple sites, of course, you need to have multiple prediction models that are for each one per site. The second use case that we can talk about, it's about the renewable energy, and also here there is the need in improving the prediction, in this case, of the wind that there is on a particular wind farm. In not actually the wind, but it is the other effect. So the production of the power that is due to the wind farm. So what they want to improve is the accuracy of the power that can be produced. There are different challenges. There are different challenges, and those challenges are related to different actors that there are into the game. First of all, there is the transmission system operator. So it is the one that has in charge of the power network. That is due to the fact that they have to balance in some way the grid with a very short horizon in order to balance the amount of power that goes into the network. And this is important because the wind power generation is not continuous, so there can be intermittency. On the other case, there are players that are the traders that want to forecast the power that will be produced in the next period to sell it on the market. And of course, there are also the wind farm owners that are interested in understanding the power that can be produced in the next period because they have to schedule the maintenance. And the maintenance, they plan to have the maintenance in period where maybe they can produce less power. So even stopping one turbine does not have a lot of impact on the possible incomes. And this is a use case by Duferco Energia. So the idea here is there are a lot of challenges, and on one side, the whole processing pipeline want to be extended, integrating the data that comes from the sensor that are available on the wind farm, and in particular, there are a sensor on the turbine, so you can estimate what are you have the actual value of the wind on the turbine. And also closer to the wind farm, and this can be used to improve the weather forecast model. So you have a fine-grained information that comes from the field. The other part is that usually WRF models are produced for winds that are in the order of 10 meters from the ground. But if you think about the turbines typically have a height that is the center is around 18 meters, and so it is important to have estimation at both height, also to have some improvement in the prediction, and of course the other challenge that they have at the application level is the possibility to adopt artificial intelligent model to learn the behavior of each single site and each single wind turbine to predict more precisely the power that can be generated. I talk about wind turbine because you can imagine that those are very large objects and they need some specific calibration. So one wind turbine to the other wind turbine with the same wind speed do not produce the same power. So this is something that it is important to link with the power production. Of course, also in this case, it is not explicitly requested, but there is the need to understand if there is the possibility to use heterogeneous resources, FPGA, in order to improve the prediction, to have a larger prediction in short time prediction. So the request on the heterogeneous resources is done, of course, at the WRF level, but also at a smaller level. Last but not least, the last one it's about the traffic modeling for smart cities. We have so this SIGIC use case. It's about SIGIC as a mobility platform that takes data from several sources, directly from the car. Those are called floating car data. So those are the GPS position, speed, and timestamp, or where the data is generated. That are produced every 10 to 5 seconds. The metric, the origin destination metrics of a city where they want to serve where they want to offer the service, the road network, and also here the possibility to introduce inside the model weather data, because you can imagine that the speed of cars when it is raining, snowing, it's different with respect to where there is a sunny days. And they are offering services that comes from what if analysis cities in order to understand what is the impact of road closure, intelligent routing, that is the one that we all use when we move by car, but also traffic prediction in order to understand a certain time what is the traffic in a specific area. The challenges from this point of view are related to the collection of the data in order to compute the traffic in 3D, so spatial across the cities, but also in the intensity of the traffic that there are in each road of the city. They want to develop and efficiently deploy on supercomputing resources a traffic simulator that gives the possibility to predict the traffic behavior ahead, and also to adopt artificial intelligence technique to learn what are the traffic patterns, in particular to give support in the traffic prediction to the simulator and to the intelligent routing service for predicting what will be the traffic at a certain time. And again, also in this case, making use of heterogeneous resources. So those are mainly the use cases that we have inside the project. On the completely opposite side, we have our the target system. So the target system that we have inside EVEREST are mainly based on the data center and supercomputing infrastructure. Within the project, we have IT4I, that is the Czech supercomputing center. So this, of course, is one of the target, also because of the workload that the WRF has. But there is also data center perspective. There is the IBM with their internal data center that is used as a possible use case. But this is a global view, but we are more interested, as we mentioned before, in understanding the usage of FPGAs. And so focusing on the server side, on the node side, we see two different types of FPGAs inside the data center. One that is connected to the main CPU, to the host, normally using PCI Express, and the other one is a different type of FPGA architecture that is not directly connected to the host, to a CPU, but is directly connected to the network, which means that in order to access to the FPGA, you don't have to pass through any CPU. Not only because the FPGA is connected to the network, but because the FPGA is completely disaggregated. So the idea of disaggregated FPGA is the internal project in IBM that is called the Cloud FPGA. So the project Cloud FPGA is the idea to have the FPGA directly accessible from the network, and as I mentioned before, having the possibility to have racks that are directly dedicated to FPGA without the need of live together with CPU server. So here in the image you can see a picture of a disaggregated FPGA rack with multiple components.
Gianluca, sorry to interrupt. It would be good if you could wrap up soon.
Yep, I will try to speed up in few minutes. So that is more or less the idea. What the guys in IBM did, not only to think about this idea of disaggregated FPGA, but also the possibility to have a software development kit, a development kit for Cloud FPGA that exposes the FPGA to who want to use without the need to design the part of the logic that is interfaced to the network. So the FPGA modules inside Cloud FPGA can be divided in two components. The first one is called shell, that actually interfaces as all the logic that interfaces with the network, so the network stack, and then there is the user logic that is the actual logic that usually we design on top of an FPGA, and the interfaces from the shell to what is called role, that is the user logic, is done considering standard XC, AXI interfaces. So without speeding up a bit, sorry for that, we saw very nice application. We saw these interesting architectures, but what there is, how can I map one to the other? Well, within EVEREST, we try to face the problem of this type of mapping. So we are not the only one. So we saw today a lot of talks about what are the best way to do this. Of course, there are problems related to the programmability. So how to limit, how to permit programmers that does not have any knowledge of the hardware, so without hardware skill, to target such type of platform. And on the other case, we have always to consider the data center cases in which there is this problem of portability, because when you deploy an application in data center, you want to be a bit abstracted from the underlying hardware. So this is something that we have to face. So the first problem is something that we are facing considering DSL and high-level synthesis tool, while the second one is something that we are facing through a sort of runtime management of the application. Let me go. To do this within EVEREST, we are developing what we call the system development kit. We use SDK, but S is not for software. That is a sort of coordinated design environment that wants to bring specifications that comes from the user with the functional and non-functional properties that are annotated on the code, the abstraction of the target hardware, and then there is the compiler environment that generates the hardware and software binaries for the CPU part and also for the FPGA part for deploying the acceleration. And last but not least, we have also a runtime part that tries to manage everything that is related to the data center context. To brief, say a few words about the programming environment, we can say that we have a programming environment that is around that start from a DSL for integrating both functional and non-functional descriptions inside the applications. And this DSL at the end, the DSL and DSL extension are then mapped onto the unified intermediate representation framework that is MLIR, that has been shown also before and talked before by Tobias. To guarantee starting from MLIR, then there are several steps that can be done. On one case, the code that need to be mapped on the FPGA is then translated in C or kept in MLIR in order to feed the high-level synthesis tool, Vivado targeting the Xilinx FPGA, or Bamboo for FPGA in general, and to integrate extended annotation in the intermediate representation. But there is also the possibility to annotate the behavior of the data to customize the memory components. Regarding the runtime environment, what we consider on the runtime environment part is that we suppose that we have the possibility on the compiler side also to generate multiple variants depending on different version of the hardware. And at runtime, the idea is to select the best configuration that is dependent on the actual hardware, but also on scenario that can be the type of data that is going to process and the requirement in terms of quality of data or quality of the output that you want to elaborate. So the runtime part is divided mainly in two parts. The first one is related to the virtualization that try to abstract the hardware resources and also offers dynamically the FPGA to different virtual machines. And the second part is related to a more application level part that takes decision about the type of version of the application and the configuration of the application that should run in a certain moment, or the multi-node management, because as we mentioned before, the application can be spread on multiple nodes, and it has in charge the scheduling of the application onto the multiple resource and actually the resource allocation. So the idea is that the runtime part is in charge of automatic deployment and configuration of the application onto the multi-node, cloud, and FPGA resources. So I will skip all those animations that makes more details about the implementation. Let me go directly to the conclusions. So that's what I showed today. It's only a brief overview of what the EVEREST project is, and it tries, as I mentioned, to simplify the use of FPGA, starting from 3 real-life use cases. As we mentioned, it's not only kernels. We are trying to understand how the big picture can be placed together if a user wants to use FPGA inside the data center. There are a lot of interesting stuff that we are tackling, from cloud FPGA as hardware resources, but also the interoperability by using MLIR. The EVEREST SDK, so all the tools that are briefly briefly mentioned before, will be made open source at the end of the project. So it's something that that you can use. We have to say that currently we are still not in the last part of the project, so there are many pieces that are already available. As example, Bamboo, Margot, dEsign, the cloud FPGA part, but there is not yet the global picture that has been finally composed. So that's something that I wanted to mention. But this is our view, and we hope that in the next year we are going to produce very nice result. So I can say that that's it, more or less.
Perfect. Thanks a lot, Gianluca, for this very nice overview of the EVEREST climbing and the project, the overall project.